lesson is going to be one of two parts, and we're going to still continue our study of polynomial, and we're going to look at polynomials with one variable today and talk about those polynomials as simple functions. So some terminology that we need to understand is, well, what does polynomial in one variable mean? That means that in your actual expression, you're only going to ever see one variable. So you can see in this polynomial, we have 5a squared plus 3a minus 2. Our variable here being a, just one variable. Now you'll have different powers of that a, but you only ever have an a in there. Another example could be 3y squared minus 2y plus 7. So you can see that the only variable that you see in this polynomial is y. A polynomial that would not be in one variable is when you have multi-variables in there, like 2ab plus a squared minus b. That would be not in one variable because you can see the representation of both a and b in there. Now that we're in just one variable mode, we can talk about a leading coefficient. So the leading coefficient is going to be the coefficient of the term with the highest degree. Now when we have more than one variable in there, we might have different terms with the same degree. When we're only talking about a polynomial in one variable, we're going to have one term that will have the highest degree. If I go back to these two examples that I have here, this degree is 2, so that makes our leading coefficient be 5. Again, in the second example, I also have a degree of 2 in my first term, so my leading coefficient would be the 3. I have 3y squareds. That leading coefficient term is going to tell us a lot about what's happening in the polynomial as we move forward. So that's an important concept to understand. Okay, so let's look at 4 different examples of polynomials. You can see that the first one doesn't have a variable to it. So when there's no variable present, we give this name of this polynomial as constant because it never changes. It remains 9 all of the time. When we're talking about the degree of this, because there is no variable, the degree would be 0. That would mean that our leading coefficient would simply just be 9. Now, when I look at this polynomial x plus 4, because it is to the first degree, this would be a linear polynomial. Anything to the first degree with the highest degree of 1 is a linear polynomial. And again, that degree is 1, and our leading coefficient would be what's in front of that. And since there is no number, we're going to assume that that's also 1. For our third example here, we have a degree. The highest degree is 2. We also have a linear degree in there of 1 also, but because the highest degree is 2, the degree of my entire polynomial is 2. We give this special function or special polynomial the name of a quadratic, and we studied quadratics quite a bit in the last chapter of how to graph them and how to solve them. So this one should be very familiar to you. That leading coefficient in this one would be 4. There are 4 x squareds. That's what makes the leading coefficient. For our fourth example, our degree, our highest term degree would be 3. We give this one a special name as a cubic function, and its leading coefficient is a 5. Anytime we go beyond 3, they don't typically have a special name. Well, actually they will when we talk about the graphs of them, but eventually we'll just call them polynomials. For our first example here, it says state the degree and the leading coefficient of 7z to the third power minus 4z squared plus z if it is a polynomial in one variable. If it is not a polynomial in one variable, explain why. So because we have only z's, it is a polynomial in one variable. The degree of this polynomial would be 3. The leading coefficient of this polynomial is the coefficient on the third degree, which is 7. And this would be that special polynomial called a cubic function. In our second example, we have 6a cubed minus 4a squared plus ab squared. Since that third term has more than one variable, this would not be a polynomial in one variable, and that would be because of the ab squared has multivariables to that. Okay, so now we're going to look at what a polynomial function looks like. Now, when we're just talking about an expression, we see the 3x squared minus 2x plus 10. When we started algebra, we would have represented this with a y equals 3x squared minus 2x plus 10. But when I write it as a function, I use that f of x notation. What that f of x notation helps us do is it helps us to import either numbers or other variables within that function. So if I wanted you to find a value for 3, what I could simply do is ask you to find for me f of 3. What that means is find me what my output value would be when x is 3. So you can see what I've done here is I've taken x and I've replaced it with 3. I'm going to do that in this polynomial as well. So what I'll have here is I'll have 3, and every time I see an x, I'm going to replace it with that 3 that I'm looking for. Minus 2 times 3, and then I'll have plus 10. So now I'll do my order of operations. 3 squared is 9 times 3 is 27. Minus 6 plus 10. So I'll have 27 minus 6 is 21 plus 10 would give me 31. And what's nice about this is I can ask you now to find what is f of negative 2. So the same idea is what I will do is I'll take that original function, and everywhere I see an x, I'll replace that original function with 2. Negative 2. So again, I would do the math simply. Negative 2 to the second power would give me a positive 4 times 3 is 12. Negative 2 times negative 2 is a positive 4 plus 10. So I end up with 12 plus 4 is 16 plus 10 is 26. So you can see real simple how it is to input into our function notation. All right, so if we look at this honeycomb pattern that we have here, it says a sketch of the arrangement of hexagons shows a fourth ring of 18 hexagons. So that means if you start in here and then count how many rings you go out, when you go to 4 rings out, it has a total of 18 hexagons. A fifth ring would have 24 hexagons, and a sixth ring of would have 30 hexagons. Show the polynomial function gives the total numbers when r is 4, 5, and 6. So what this is the function for the number of hexagons within the rings. So how we watch this function unfold is we're going to find f of r when r is 4. So we're going to replace that r everywhere with a 4 into this quadratic function. So when I do this quick math here, so I do 4 to the second power would be 16 plus, or times 3 gives me 48 minus 12 plus 1 says within the fourth ring out, we're going to have 37 hexagons total. Now that's counting what's in that fourth ring, and it's counting everything inside of that fourth ring as well. So the fourth ring has 18 hexagons, but all of the other ones inside would add to be 37 hexagons total. We could do the same thing for f of 5. So we're going to do 3 times 5 squared minus 3 times 5 plus 1. We do that calculation doing the exponents first. I'd have 25 times 3 is 75 minus 15 plus 1 would give me a total of 61 hexagons. And the last one they want us to do is f of 6. So we'll do 3 times 6 squared minus 3 times 6 plus 1. And you could put this into your calculator exactly like that using the parentheses for your input. And that would give us a total of 91 hexagons in all. So we could actually take this out as far as we wanted to go. And if we wanted to go all the way to 25 rings, we would simply replace our r with 25. Of course, this math gets a little bit harder to calculate, but we would take 25 squared times 3 minus 75 plus 1, and that would give us a total of 1,801 hexagons total within 25 rings on a honeycomb. So you can see how that works with inputting numbers. Let's look at our last example for today. So our last example is using several polynomials here. I'm using the polynomial b of 2x minus 1 minus 3 times b of x when this is our function. Our function is b of m is equal to 2m squared plus m minus 1. So we're going to refer back to this every time. So when it's asking us to find b of 2x minus 1, my input will, instead of being a numerical value like 2 or 3 or 25, we're going to input 2x minus 1. So everywhere I have an m, I'm going to replace that with 2x minus 1. So I'm going to find first b of 2x minus 1, which gives me 2 times 2x minus 1 squared plus 2x minus 1 minus 1. So I'm finding this first part, and we're going to simplify. Then we'll take that minus 3 times b of x. So you can see here I have a little bit of work to do. I have to square this binomial 2x minus 1, and then I'll multiply by 2. So when I take 2x minus 1 and square it, I have to multiply that by itself. So a little bit of math here. I'll do some foiling. I'll have 4x squared. My outsides will give me negative 2x. My insides will give me negative 2x, which simplifies to be negative 4x. And my lasts will give me plus 1. Then we'll multiply that 2 through by distribution, and that will give me 8x squared minus 8x plus 2. Then I'll have to add a 2x minus 1 and subtract a 1. Now I'll collect my like terms. So I'll end up with 8x squared, and I'll have a negative 8x plus 2x gives me 6x, negative 6x. Then I'll have a 2 minus 1 minus 1 that I need to collect, and that will give me simply 0. So I'll have 8x squared minus 6x for my first term, which is b of 2x minus 1. Then I'm going to go through and I'm going to multiply or subtract from there 3b of x. So minus 3 times b of x means that I'm going to have to replace x in for all of my m's here and then multiply that by 3. So I'm going to take negative 3 times the polynomial 2x squared plus x, to replace my x in there, minus 1. So I'll distribute that negative 3. That will give me negative 6x squared minus 3x plus 3. Then I'm going to put all of this together down here in the end because remember we had to subtract these two. So I already distributed that negative 3, so I'll just collect my like terms. I'm going to have 8x squared minus 6x minus 6x squared minus 3x plus 3. I'm just taking these two and putting them together now. With a collection of like terms, that's going to give me 2x squared. These two linear terms will give me negative 9x, and I will end up with just a constant of positive 3. So altogether, plugging in the two separate pieces, first the 2x minus 1 gave me 8x squared minus 6x. Then I took a negative 3 times b of x. So my b of x was 2x squared plus x minus 1 times my negative 3 left me with negative 6x squared minus 3x plus 3. Then I took these two pieces and collected their like terms, giving me the polynomial 2x squared minus 9x plus 3. One final statement I want to remind you of. When we're working with these functions, when you plug in a number into these functions, your output is going to be a number. So see, the constant 6 gives you out the constant 91. When I input 25, my output was 1,801. But in this last example, when my input is a variable or my input is an expression, my output becomes an expression. So you will see that I don't have just one number as my answer. I have an entire expression as my answer. So that's a little bit of something to think about. If you input a number, you output a number. If you input an expression, you're going to output an expression. All right, look for part 2 tomorrow in tomorrow's lesson.